push. Yeah. I can hear myself. So I turn it off.
Yeah.
Okay, welcome everyone to session number 9. It's going to be devoted to anti-chain strings and graphs. And the first talk in this session will be given by Pavel, and it will be on the paper called Anti-Chain with sat and tries.
Thank you for the introduction. Good afternoon. Some time ago, we have started to draw automata, thinking about them, simplifying them, before modeling various problems with them. And finally, we need a fast model checking algorithm to resolve those problems. So our work, the work of me, Pavel Vargovčík, and my supervisor, Lukáš Holík, is about the model checking part, using the anti-chain algorithm with a SAT solver enhanced with trias. So the input of our pipeline is some practical or even generated problem. Then from this input, we generate a symbolic alternating finite automaton, AFA, which is small. The generation is linear, so it is small. And then we continue by checking the language emptiness of the automaton. And the answer is empty or not empty. So all the data structures here are small. The problem, the automaton, and the response. The only hard part here, and it's a very hard part, is the model checking, which gives us space to play around with various algorithms. Which I think it's not the case for more traditional approach where the non-deterministic finite automata are used. So already the intermediate data structure is huge, and there's less space for optimization. Yeah, like you can use some implicit representation of it. Yeah, on the fly. So that's the first approach. Basically, you have some small representation and generate something on the fly, and yeah. Okay, that's yeah. You don't need to generate it all explicitly. Yeah, I agree. So yeah, our definition of an AFA is good for big alphabets and big transition relations. We have a set of states, and there are configurations which are sets of these states. And there are exponentially many configuration, and they correspond to NFA states. That's why NFA is exponentially larger if it is explicitly given. Then we have symbol variables, and again, sets of these symbol variables or valuations. There are exponentially many. And what connects states and variables is the transition function, which is just a Boolean, which is a mapping of a Boolean formula that is positive over states and positive or negative over variables to each state. So here we can see that, for example, the transition function of the state Q2 is Q3. Very important thing is a transition from a configuration to another configuration under a symbol A. So the predecessor K transitions to a successor L under A. Whenever we take or we view A and L as an assignment, as a valuation of variables and states, if a variable is in this set, then it is assigned 1, otherwise it's 0. And under this assignment, all or transition formula of all predecessors must be satisfied. So this is a transition. Let's look at some examples. Where should I? This part works. I cannot go. Does it work already? Okay. So here we have some examples. For example, the configuration Q2 transitions into Q3 under any symbol, basically, and Q5 transitions into an empty configuration under valuation, for example, of V1, because this transition formula is then satisfied. And for example, Q1 transitions as well into an empty configuration when V1 and V2 are both 0, because then this is 0, this is 1, this disjunction is 1. So the transition formula is satisfied too. The last portions of the AFA definition are the initial state, which is Q1 in our case, and a set of final states, which can be empty, which is our case. So the language emptiness question is whether there is an accepting run. What is an accepting run? A sequence of transitions from the final initial configuration to a configuration that contains only final states. Is there an accepting run here in this example? Yes, very trivial one. So how do we check this emptiness? This language emptiness. Naive basic approach is through graph reachability, which is like we have a space of configurations, which is a graph where edges are the transitions, and we search a path from the initial configuration to the final one. We are going backwards. It's, let's say, we implemented it like that. So I will describe the backward search. We start at the subsets of final states, find unvisited predecessors of visited configurations, and check at each configuration if it is initial. If it is initial, then the automaton is non-empty. Otherwise, if we exhaust whole reachable state space, then it is empty. But alternating automata have a nice property that with which we can prune some parts of the search space. It basically says that we can shrink predecessors and inflate successors, and the transition relation remains, it is preserved. So that's why we can or work with an anti-chain algorithm where we start only at F, not at all its subsets. If before we were pruning out predecessors that were visited, and now we prune all predecessors that are subsumed. So it means any of their supersets have been visited. And the final, or lastly, we don't check for the exact initial configuration, but if any of supersets of the initial configuration is reachable, then the automaton, the language is non-empty. How do we look for predecessors? We have this transition formula, and everybody knows state-in transformation. It creates some clauses, and we don't force the transition formula to be satisfied, we only store these links from states to the transition formula, and then we check if they are satisfied or not. So we do this for all parts of the transition formula, or transition function, sorry. And we connect it all together. And then we look for predecessors using SAT. So let's find predecessors of a configuration L, which is an empty configuration, so it assigns zeros to both states. First, we evaluate, we use this valuation. Then we run the SAT solver, which finds a solution. And finally, we extract the predecessor from the model returned by the SAT solver. So the transition formula of Q1 is unsatisfied. For Q2, it is also unsatisfied. So the predecessor doesn't include any of those states. Do we like this solution? No, because first, it is already a visited solution. So it's for sure subsumed. And also a greater solution exists, which would immediately subsume this solution. So it is not useful. For this, we use so-called SAT with preferences, which is not which is a known thing in the SAT world. So I will not go into detail, but it's some modification of the heuristic, of decision heuristic, and also there is an incremental SAT used in this. So yeah, we set the preferred literals to the image of the delta function, so to these two variables, and the SAT solver tries to or prefers ones on these variables. So, and moreover, it prunes out all the solution or all subsets of previously found solutions. So we get this as a bonus, that our subsumption check is handled by the SAT with preferences. Yeah, so this way we have found a better solution and our problems disappear. So let's recapitulate the anti-chain algorithm. First, we start with the final configuration in the work list. We check if it is initial or not. Then we also update this formula that prunes out that will prune out subsets of F in the further search. And then we process the work list. For each successor, we look for unsubsumed maximal predecessors, and also this procedure make them visited. It adds them to this part, and yeah, so we check for initiality and process the work list again. So these are the parts that we were just talking about. So we evaluate the successor. We have this input CNF formula here. Preferred literals are these two, and yeah, SAT with preferences returns some model from which we extract predecessor. Yeah, so this way we have beaten the problems with unwanted SAT models. But a new problem occurs, that the field visited is very, very big, and the SAT solver is therefore slow. So We have viewed this problem from another perspective, we have viewed this as a subset query problem, not as a SAT problem. And we did some research that the TRIA data structure is very good for solving subset queries. So we tried to integrate TRIA into the SAT solver. Yeah, the rest of my talk will be about SAT. So here we have 4 clauses, and the TRIA representation just detects the same prefix of these 2 clauses and shares the prefix. In our benchmarks, the TRIA was finally 8 times smaller than this clausal representation. And there are other differences in the CDCL of clauses and TRIA. So at clauses, we have 2 watches at 2 distinct arbitrary non-zero literals. With TRIA, we want to make use of this prefix sharing as much as possible. So we watch 2 distinct topmost non-zero literals. There is no reordering happening as it is for clausal SAT. After 0 is assigned to a watched literal, we re-establish the invariant by scanning the whole clause here, if there is a better non-zero place for the watch. While in the TRIA, we scan only the rest of the clause because thanks to the topmost part of this invariant, we know that there are no non-zero places above watches. If it is impossible to establish the invariant, we trigger unit propagation or conflict. And undoing of watch position is not necessary for the clausal case because unassigning a value from a literal doesn't violate this invariant because there are no new 0 literals present, but it is not the case in here with TRIAs, because if we, for example, unassigned this 0, the topmost part of this invariant, the watches will not be at the topmost non-zero places anymore. Let's see it all in action here. Sorry. And we use a system of snapshots to backtrack or undo the decision levels. So at the end of the decision level 0, we had the 2 watches at the topmost non-zero literals. We have nothing more to do, so we make a decision. We assign 1 to the variable v6, and I didn't tell it before, but our SAT doesn't include only TRIA, but also clauses. And some TRIA is used only for the big anti-chain part of the of the clauses, but there are learned clauses and the input. So some external clause has caused an assignment of 0 to the variable 1, which caused now the rear guard had to move down, and the front guard front watches have been pushed further down too, which and the invariant is reestablished. Also, we have created a snapshot that says that in the previous level there were 2 watches that we have deleted, and we have created 3 new watches here. Then the unit propagation continues. Another clause assigns 0 to the variable 2, and the watches are moved further down. The rear watch pushes F2 to a good place with non-zero literal, But here it cannot happen. There is the invariant cannot be established in this clause. So we have to unit propagate. And another clause continues with unit propagation and causes a conflict. Then some conflict analysis continues. And we have to backtrack by, we do it by recreating the deleted literals from the previous levels and deleting the new literals from the current level. So this is how unit propagation works for trias, but SAT with preferences must be able to add new clauses to the tria. So if we want to add this new clause, what do? We could look for the shared prefix and add the clause here, but we can do better because we can reorder the clause. Actually, we find the longest shared prefix in the tria and add smaller, less literals to the tria. This is almost for free because I will not go into detail, but we use solver state to detect the longest shared prefix very cheaply. Also, another problem is that the snapshots need to be updated because they are incompatible with the new shape of the tria, which is done using simulation based on decision levels of assignments to variables. So this is all. And now, how does the use of tria contributed to the model checking time? There are some exceptions, but not too severe. But mostly it has quite significantly improved the model checking time. Here we can see very good set of benchmarks. We have compared the technique also with other implementations of alternating automata model checking or the NFA approaches. And yeah, there are like ABC is still statistically better, but we have solved 159 new instances. Also, we've been also statistically better than the NFA construction MATA tool, and in the future we could implement the tria into the SAT solver of ABC or of another maybe another IC3 implementation, which could make it which could bring improvements here too. So the future directions are, as I said, application of the tria in IC3, trying all the algorithms in backward and forward manners. We could, we have, as we were touching the very basics of CDCL, we have used very basic Minisat solver. So we could try to implement it somehow efficiently in the new top performing solvers with many features. For example, I think that a local search could help this problem. So, and yeah, the tria could be applied also in general SAT solving. Thank you for your attention, and I'd be happy to answer questions.
Thank you. Do we have any questions? Yes, we do. Moshe?
So if you go back to DPLL, they proposed two heuristics for speeding up search. One was unit propagation. The other one was subsumption. Now, subsumption was abandoned as a practical heuristic because the cost of subsuming did not compensate for the cost was too high. It did not speed up such solving enough. So we don't do subsumption today.
But it's subsumption
of clauses. You can do subsumption for clauses, and we don't do subsumption today usually because it's too expensive to do subsumption.
Yeah, but my
why does it work here and it doesn't work for such solving?
My subsumption was not about subsuming clauses.
No, I'm asking you to explain to me the intuition. Why subsumption fail for such solving and it succeeds here? Is there an explanation?
Like in SAT solving, I think you have few more clauses. It's not a big deal, but in AFA model checking, you want to the state space is huge, and we want to cut pronounce.
Today we are dealing with when you have huge formulas, so subsumption could save, but the point is the cost of subsumption is just too high. And here it's not. I never understood why interchain work. Why does the cost of subsumption? Yes, you cut down the state space, but you have to spend. You have overhead of doing subsumption.
If we were not doing subsumption, we check if we visited exact configurations before, and it is. I think it is in no way simpler to check visitedness of exact configurations towards visitedness of subsets or supersets.
I see.
Yes, so there's like two works which also use tries actually. Even 30 years back, there was Sado, which actually had internally tries, and it actually invented this head and tail pointers. And then there was a preprocessor by Fabio Zumenzi who also had tries. I think it was called Alembic. Did you compare it against their way of doing?
Yes, it is in the paper, and Sato was. I don't know why, but I didn't try the implementation or debug it, but in the paper they state that the rear guard or the top, there is one guard or watch going from the top and one from the bottom. I don't understand why, but I feel that this is the biggest difference. And and the Sato was purely based on tria. So I think there was a problem with learned clauses, with forgetting learned clauses. So they, prior to implementing these learned clauses, they have dropped the support for trias and use only the clausal version.
Okay, do we have any other questions? I think we still have time. Okay, I have one question. Why did you decide to use prefix trees? Why not some sort of decision diagrams, say BDDs or SDDs?
There are hundred thousands of those clauses, and we did some experiments with LV BDDs that could be used for this, and they were exploding after like 50 clauses were added. So
okay,
of those sizes, so it was impossible. Then we did some experiment with and or graphs, which are basically like SAT clauses, and covering sharing trees. We were comparing other approaches, and this tree seemed the best, and it was as a bonus, it was very simple.
Okay, thank you. Okay, let's thank the speaker again.
Thank you.
And the next talk will be on cooking string integer conversions with noodles. And the talk will be given by Uri. Sorry, I won't pronounce the last name. I don't. Sich. Yes.
Is the mic is working? Thank you for the introduction. I'll be talking how we cooked string integer conversions with noodles, or in more boring terms, how we extended our string solver Z3 noodler with string integer conversions. So first, what exactly are we doing? What are we solving? We are working on string solving, which is we have some SMT formula where the variables, for example, x, y, z, are over string. They are string variables. And then we have predicates such as equation between strings. Here on the right side, you have concatenation of strings. These equations, some regular constraints where we say that string x must belong to some regular language, some length constraints, which also introduce some arithmetics here. And we can also put some more complex string operations such as contains or replace. What is the motivation behind this? Well, we could use such formulas in, for example, analysis of string manipulating programs. Where we have some program and we can transfer it into string, this sort of formula, and ask the string solver if it's sat unsat, which means if the assert here is reachable or not. More interesting example is in Amazon. They actually use string solvers, as far as I know, in access control policies of in the cloud, where some users have some can have access to some resources, and they have this sort of format, and they transform it into a string formula and ask string solver if it is satisfiable or not. And by this, they decide if the user can access it or not. So I'll give you a quick overview of our previous work on string solving, because we are building upon this in this work. So we have this sort of formula. So we started with some paper in FM, last year FM, where we took equations, regular constraints, and we introduced a decision procedure for solving them, which tightly integrates these two constraints. And it works with languages of variables. It represents variables as their languages. It uses something we call noodlification. I will explain this a bit. And we refine these languages until we get to something, until we solve it. And what's important is it is complete for the chain-free fragment, which is largest, or maybe one of the largest decidable fragments in string solving. And we had some prototype implementation in Python, and it looked like it had very promising results. So we took this, and in Uppsala, we show how we combine this decision procedure with an older algorithm for solving strings. We call it here align and split. And by combining it, we could solve then length constraints, and by extension also these equations and some of the more complex operations. So in this work, we also use some linear integer arithmetic encoding. I will talk about it a bit. And what's important, it's still complete for chain-free fragment. And we implemented it in a proper string solver called Z3 Noodler. So that was the previous work. So we can solve these, but from the complex operations, we can solve only some of them. And one of them which we couldn't solve were string integer conversions, such as toInt from int or toQuote from quote. ToInt from int takes a string and transfers it into an integer, or from int takes an integer and transfers it into a string. toQuote from quote takes a character and returns its code point, Unicode code point. So for example, for A, it's the ASCII value. So I will start with how the decision procedure from FM, the first one, worked on this example. We have two equations and some regular constraints. The alphabet is just AB, so it is simple. And we take all the regular constraints first and collect them into a language assignment, which is just a assignment of variables to their languages. We represent these languages by automata, by non-deterministic finite automata. So we have some equations and this language assignment. And then we look at the equations and use them to refine this language assignment, the languages in the language assignment. And let's take the first equation. And we know that if we have a solution, some assignment B, then the concatenation on the left and right side must be the same. So actually, the languages on the left and right side should be also the same. So we can use this. We take the right side and refine the languages on the left side. How we do it? We use something we call noodlification. That's where the noodles come from. Here is an example of how it looks on automata level. I won't explain this because I don't really have time. But basically, we end up with some noodles, N1 and N2, which are used to refine the languages. So for example, in N1, we refine X to language just containing A, and Y to this language which repeats BA. And then we have the same thing on both sides. In N2, we get something like this. X is epsilon, so Y must be everything that is on the right side. We can now select any of these noodles. Let's say we select the first one, and we update the language assignment. And we continue like this. We take the other equation. Here we end up with only one noodle, which refines the language of W to A. You can now see that the languages in the equations match. And we prove that this is enough to decide that the formula is satisfiable. And we call the language, this language assignment, we say that it is a stable solution. So that was FM. And then we extend this decision procedure in UPSLA because FM can only handle regular constraints and equations, and we want to handle all other constraints. So for these equations and the more complex, some of the more complex operations can be reduced, at least partially, to some simpler constraints, which we can solve. So I won't talk about them. I will talk about lengths. This is important. How do we handle lengths? We create an arithmetic formula that encodes all the possible lengths of words in the language assignment. So if I return back in, for example, for a variable y, we have that all the possible lengths are just the even numbers. So we can create an arithmetic formula that says the length of y must be even. The problem here is that the stable solution, the language assignment, does not keep dependencies between the lengths of variables. For example, if the length of y turns out to be 0, then on the right side, the length of z and u must be 1, because then this part is empty. So how do we solve this? We combine noodlification with the already mentioned align and split algorithm, or that is an existing algorithm. And I will show how it works on very simplified example. This is not exactly how it works in the solver, but it's enough for understanding this work. Again, we have some equations, and I will explain on this example. We have some equations, one regular constraint, and some length constraints. Again, we have this language assignment, and we apply this align and split algorithm, which takes this equation and it splits it. We get exact solution by splitting W to concatenation of V1, V1, and X is also becomes V1. And we use noodlification here to get the language of V1. And this was basically the splitting. And by doing this, we also need to introduce something else, some third thing in this is the language assignment, and this is something we call substitution map. We take the equations that have only one variable on the left side, and we create, we say that X must be substituted by V1. And basically we do this also with this equation and this equation. And we end up with we process all the equations, so we have a stable solution. But now the stable solution is not only the language assignment, but also the substitution map. Here you can see that x is replaced by v1, w is replaced by v1 v1, z is replaced with v1 y. And then we encode the possible lengths of variables by looking at this stable solution and taking each part and basically doing this. For v1, we have the language, so we just say in the language we can see all the words must be larger or equal than 1, so we do that. For y, there is no constraint, so it just must be non-negative. And for the substitution map, we just do this simple thing where we just say that what is on the left must have the same length as what is on the right. And now we take the arithmetic part of the initial formula with this Lia formula encoding all the possible lengths. We get this, and ask if it is satisfiable. We use some Lia solver here. It's not our implementation. And we get the model of the length, and we use these lengths to choose first the words from the language assignment so that we have the correct length. So for v1, we choose A because it should have a length 1, and it is in this assignment. And then we choose then we compute the models of the other variables from the substitution map. So this was all what we done in previous work, and now I can talk what we did in this work. So we have this decision procedure that returns a stable solution. We also have the arithmetic part of the initial formula, which was here this part. We also have the formula encoding possible lengths, and we also have some set of conversion constraints we want to handle. So what can we do? Well, we do basically the same thing for conversion constraints as we did for lengths. We encode them as in arithmetic formula and then use it to get the models. So for each conversion constraint from this set, we encode it in some Lia formula phi Then we take the conjunction of them, add them to the initial part and the formula encoding the possible lengths, ask if this whole thing is satisfiable. If it is, we have a solution. If it isn't, we try to look for some other stable solution. And if we can't find any stable solution, we say it's not satisfiable. So I will now talk about how we handle different types of string integer conversion constraints. So for toInt, the semantics of these conversion constraints are here. For a valid x, some string x, if it contains only digits, it's valid. Then the result is the number represented by x. If it contains some non-digit, it is invalid. So we just return -1. And according to stable solution, we have to handle two distinct cases. Either x is mapped to some language in the language assignment, or it is substituted by some concatenation of variables in the substitution map. So how do we handle the case when it is in the language assignment? We have some language lx for x, and this formula, or this phi, should encode that the result of toInt x is actually the result of applying toInt on some word from this language. This is generally not possible with linear arithmetic. We would have to use something nonlinear. So we add really strong restriction on the language lx. We need lx to be finite. It seems like this is a really strong restriction, but we mitigate it with some other approximation methods. Also, we generate some axioms to handle this also. And it looks like it's enough to handle most of the benchmarks. So now we have a finite language. So what we can do, we can just iterate over all words of this language and say that the result of toInt x must be equal to the applying of toInt to some word W. However, there are some problems with this. One of them is that this formula would not keep correspondence between the length of the string x and the value of toInt. Well, this is easily solvable. We just say that if toInt x is equal to application on the word W, then its length must be also the length of the word W. The bigger problem is that this formula would be really large. Like if the language is large, which can happen, then it would blow up. And also we tried this actually, and it really did blow up. So instead of encoding each word, we encode some continuous intervals of words. So I'll show it on an example what it means. We have the language LX. There are 3 continuous intervals, and we create the following formula. We take the first interval, and we say that toInt x must be in this interval, and also we relate the length of the words in this interval. So we say that the length of x must be 1. Similarly, for the second interval, again, it must be in this interval, and the length must be 2. For the third interval, the same thing. It must be in the interval, and the length must be equal to 3. This is very easy to implement on the automata level. There's just some, you just have to think about it a bit, how to get the continuous intervals. It wasn't very hard. And also, I was talking here about only the situation when LX was only contained valid cases, valid strings for the conversion. I ignored the invalid cases. It just makes the formula more complicated, but it's not very, it's just technical stuff. So I won't explain it here. So this was the case where X was in the language assignment. And now what if it's in the substitution map? So X should be replaced by some concatenation of string variables. Well, I didn't talk about this, but in stable solution, we assume that if some variable occurs on the right side in the substitution map, then it is not substituted to. So it must be assigned to some language LXI in the language assignment. So for each of these variables, we have their languages, and we already shown how to encode the result of applying toInt for them using the interval method from the previous slide. So we can just encode them, and then we can use these values to encode the value of toInt x. And we do this by taking each combination of lengths of these variables. So L1 is some numbers, is some possible length of some word from the language LX1. So we take all these combinations, and for each of them, we create this sum. It just says that the result of toInt, for example, if I look at xn, toInt xn should be at the end of the number represented by toInt x. So this part will be actually 0. So we will get 1 here, and we will have that toInt xn plus toInt xn minus 1 times 10 to ln, which just means that we move the toInt xi minus 1. We just move it enough places in the numbers so it's in its correct place. We also relate the length of the variables on the right side, so we get correct length. And we just then take this disjunction of these equations, and that's it. Again, I ignored the invalid cases. It just makes it a bit more complicated. I won't explain it here. So we know how to encode toInt, and there was also tocode. So again, semantics of tocode is simple. If x is character, if it's a valid, then k is the code point of x. And if it's not character, if its length is either larger than 1 or it's 0, then the result is -1. So again, if you look only for the valid part, here we have very much simpler situation. The language LX, the valid part are just characters of this language. So it will be finite. So we have no problem with infinite languages, and we can just do the similar thing. We can iterate over all the characters of the language and say that to code X must be actually code point of some of its characters. There is still a problem with the blowup I was talking about because the alphabet is really large. It's basically Unicode. But we noticed that usually in the formula, the explicitly used characters, the set of explicitly used symbols is usually very small. So what we do, we take this set of explicitly used symbols, it's small, and add to it a special symbol delta, which represents all unused symbols. And we work with this much smaller alphabet, and we just need some special handling for this delta. I won't really explain it, but it's also not very complicated. Also, again, I didn't talk about the invalid part. It's just, again, some technical stuff. And what's important, we also need to keep the correspondence between to code X and to int X. We could have both these conversions at the same time. Again, we can encode this into some Lia formula, and it's also not very complicated. I was talking about to int to code. We can also transform from the other direction. We have a number, and we want the string, but it's actually the same thing because instead of constraining the result, because here we were constraining k, we wanted to have the k in the formula. Here we will just constrain the argument from the result because we have the languages for the result. And so we use the same encoding. There is just some slight difference for invalid cases. So we implemented this in our string solver Z3 Noodler. This string solver is based on SMT solver Z3, in which we took their string theory solver and replaced it by our solver, string theory solver. We use their Lia solver for the encodings. We also use Mata library, which was already mentioned by Pavel, which is our library for handling finite automata. If somebody wants to try it, please do. We would like to see people using it. And just some add, we won this year's SMT Comp string division with this solver. Here are some results of some experiments. Compared Z3 Noodler with other string solvers, or actually SMT solvers with CVC5 and Z3 on SMT benchmarks, which contain some string integer conversions. Here you can see how long it took to solve. Down here is how long it took to solve the formulas for us. Here, how long it took for CVC5 or Z3. If it's in this part, it means we were faster. And you can see there are a lot of formulas here. So we are often significantly faster than state of the art. And in conclusion, so what we did, we extended our existing decision procedure with string integer conversions. We implemented it in our string solver. We've shown that we can beat some existing solvers. I haven't mentioned this, but this extension is still complete on the chain-free fragment I already mentioned at the beginning, with this restriction that for toInt, the language must be finite. And here's some stuff we are currently working on. We want Z3 Noodler to generate models. This is nearly done. And also we want to handle some harder operations, some harder string operations. Okay, that's all for me. Thank you for the attention.
Thank you. Do we have questions? We have some time for questions here. Well, I have a quick question. Did you maybe try to implement this in CVC? Because
We were
according
actually
to your plots, it looked better than that.
we were thinking whether to implement it, use D3 or CVC5, and our colleague already had some idea how to do it in Z3 because there is some older solver called Z3 Trau. So we just chose Z3, and that's it. But we are still thinking of better to try it in CVC5.
Okay, thanks. And any questions? No, then let's thank the speaker again. And the next talk will be called Starting Coding of Partial Ordering Models for Graph Coloring Problems, and the talk will be given by Daniel Faber.
I think so. Yeah, it's on. It's on. Right. All right. Wait, how does this microphone work? Yeah. So thank you for the introduction. Today I wanted to talk about our paper that was written by Ala Jabrailov, Petra Motzel, and myself. And yeah, so going into it, I first wanted to introduce the problems we're dealing with. So the graph coloring problem, which is a very famous problem in graph theory. Well, the problem is we are given an undirected, unweighted graph, and then we want to find a coloring of this graph that is a mapping from the vertices to the set of natural numbers, such that if two vertices are connected by an edge, we need to assign different colors to them. So the natural numbers which we assign are called colors. And yeah, for example, for this graph here, we can see an optimal coloring. We can see for every edge, the vertices have different colors. And yeah, now the overall goal is to find an optimal coloring, which means that we want to minimize the maximal assigned color or equivalently the number of colors used. And the value of an optimal coloring is also called the chromatic number of a graph G. And for this graph, you already can see that this is an optimal coloring because we need at least 3 colors because of this triangle here. And now a variation of this problem that we also considered was the bandwidth coloring problem, where we now have edge weights. And now for a coloring, we need to enforce that vertices that are connected by an edge, the colors of the two vertices need to differ by at least the edge weight. And the goal is then once again to find a coloring that minimizes the maximum assigned color. So in this example, we can see that this is an optimal bandwidth coloring for this graph given these edge weights. We can see here, for example, these two colors would need to have colors that differ by at least 5, which is the case because the difference between 2 and 10 is 8. And yeah, so why are we even interested in these problems? So graph coloring has a lot of applications in a variety of areas. One of the most prominent one is scheduling on timetabling, where we want to assign time slots to events without assigning the same time slots to conflicting events. But it has also applications in register allocation, sparse Jacobi matrix computations, and many more. And specifically, the bandwidth coloring problem has application of frequency assignment problems, where we want to assign frequencies to antennas such that the frequencies between neighboring antennas differs strongly enough such that there's no interference between two antennas. And now the problem is that both the BCP, the GCP, and the BCP by extension are NP-hard, because the BCP is just a generalization of the GCP, where we just have unit edge weights. And it is also a hard problem in practice. So it's also
and be hard to find a constant factor approximation for these, for these problems. And yeah, because they're so because problems are so popular, there's also a large body of literature on algorithms for these problems. For the graph-going problem, at least, there are heuristic as well as exact approaches, and some of the more popular exact approaches include methods that are based on integer programming, of course on satisfiability testing, and on dynamic programming, but this will not be, the last one will not be important for this talk. And for the bandwidth calling problem, as far as we know, most of the work has focused around heuristic methods, but there has been recent work by Diaz et al., where they propose methods based on integer programming and constraint satisfaction programming. Yeah, and now I wanted to go into some of the known ILP models for the graph-going problem. So, I mean, for those of you who do not know what integer programming is, quick recap: it's just we want to find we have some integer variables, and we want to optimize a linear function over these variables while satisfying some linear constraints. And in this case, this is a 0-1 integer program. And I would say this is like the most straightforward model for graph calling. Yeah, basically let H be some upper bound on the chromatic number. So the set of used colors can be described by colors 1 to H. Then we have a variable for each pair of vertex and possible color. And these variables just indicate if we color some vertex V with color I. And additionally, we have some variables that indicate if we use a color I for every color. And then the model is fairly straightforward. So we want to minimize the number of used colors. We want each vertex to be assigned to exactly one color. And we want for each edge that, and each color that at most one of the incident edges has this color. Otherwise, we would have a conflict. And now, one of the drawbacks of this model is that it contains symmetry, which is due to the fact that the indexing of the colors is arbitrary. So, for example, if you imagine we have some 5 coloring of a graph, then we can get an equivalent coloring by swapping if we consider the vertices that are colored with 3, for example, and the ones with 4, by just assigning all the vertices with color 3 now with color 4 and vice versa. So basically swapping the colors, we get an equivalent solution. And yeah, to break these symmetries, there have been some symmetry breaking constraints proposed by Mendes, Diaz, and Zabala. And the main idea of these equations, I won't explain it exactly, but the idea is that we sort the color classes by the smallest, by the vertex with the smallest index. So what these constraints basically enforce is that if we have some color I, then the vertex with the smallest index has a smaller index than the smallest index in color I plus 1. And I will come back to these equations later. But first, I wanted to go back to the bandwidth calling problem and the models proposed by Diaz et al. Because they're just some slight modification of these assignment models. I won't go much into detail of this Z variable. That's just a slightly different possibility of modeling the objective. But the main modification here is that we now have a constraint not for every edge and every color, but for every 2 pairs of colors that have a distance of less than the edge weight. And then we need to enforce that the 2 vertices cannot have these 2 pairs of colors at the same time, because then there would be a conflict. Yeah. And now the thing was that usually in our department, we mainly work with these ILP models, but then someone made us aware that basically for these graph calling problems, the the SAT solvers seem to perform really well. So we started to look into SAT solving. And fortunately enough, these assignment models can actually be translated very easily into a SAT encoding. And so this is not a new encoding. This is also very well known in the community. Yeah, basically it's just the same as the ILP model, we just need to substitute like the sums with disjunctions and the minus signs with negations, and we end up with the SAT model. And it's a bit different because this constraint only encodes that each vertex is assigned to at least one color, but one can also add at most one constraint to encode that each vertex has exactly one color, which is not strictly necessary, but it can reduce the search space. And we just use the sequential count encoding for that. And the same can be done for the model for the bandwidth calling problem. So this has not been has not been done yet, but it's also very simple because the edge constraints are very similar to the regular assignment model, just that we now have constraints for every pair of color. But now I want to go into the main model of this work, which is the partial ordering model, which has been proposed by my colleagues, at least the ILP model some years ago. And now the idea of this model is that we no longer have variables that directly assign colors to vertices, but we have these variables again for every pair of vertex and color that now encode if a vertex is assigned to a larger color than I or not. And then we say that the vertex is larger than the color. For example, this vertex C would have variables yc1 equal to 1 because it is larger than 1, and then yc2 to 4 equal to 0 because it is not larger than 2, 3, and 4. And then the coloring is implicitly given by for every vertex, the smallest color that is not smaller than the vertex. And yeah, additionally, we have this isolated dummy vertex Q, which is just used to, which we enforce to have the largest used color, and that is just used to formulate the objective. And yeah, this is the model in detail. Basically works like this. So the objective can be modeled by the number of the set of colors that is not larger than Q. Then for those two constraints, the first one just encodes the boundary of the ordering. The second one just the transitivity of the ordering. The next two just enforce the edge constraints. We can basically see that this term here is exactly 1 if the vertex U is assigned to color I, because then the next smallest color is already smaller than the vertex, and but the color I is not smaller than I. So if this is 1, exactly if this is 1, vertex U is colored with color I. And for color 1, it's a bit different because then there is no U0 variable. And this just encodes that Q has the largest used color, so that the objective is correct. Yeah, I think this I already explained basically. And now the good thing is, because we have this relationship between the variables of the partial ordering and the assignment model, we can actually adapt all the strengthening constraints of the assignment model for the partial ordering model by just substituting the variables. And then we end up with these symmetry breaking constraints. Yeah, and now what basically happened was that we are made aware that, so in the paper from 2018, we have seen that a variation of the POP model performed better than the assignment model, at least for the ILPs. But after that, we were made aware that actually the SAT solvers seem to perform really well on these graph coloring instances compared to the ILP models. So we wanted to see, okay, what happens if we just plug these partial ordering models into SAT solvers. And the good thing is that these models, that as similar to the assignment model, the POP models can also be very easily translated into SAT encoding, because we once again only have binary variables and only 0, 1 coefficients. And then we end up with this analogous encoding. And now it turns out that these encodings were actually already known in the SAT community, and I thank the reviewers for pointing that out. But still, we wanted to see what happens if we combine them with the same symmetry breaking constraints and compare them to the directly compare them to the ILP models. And yeah, so that's what I'm going to do now. Because the problem is, if we look at the symmetry breaking constraints of the POP models that we previously, they cannot be translated into SAT as easily as all the other constraints of the POP model anymore, because of this sum here with these negative coefficients. So there are some ways, but we actually found out that if we drop this term here and have these relaxed constraints, we can prove that in combination with these other constraints, which basically enforce that a variable cannot have cannot be assigned a color with a larger index, we have the same symmetry breaking constraint, the same symmetry breaking as with the original symmetry breaking constraints. And the advantage of these new relaxed constraints is that these once again can be easily encoded into SAT by just substituting the sum by disjunction. And that's for the graph coloring problem. Now, I think the more interesting thing was actually for the bandwidth coloring problem. And that's also the main reason why we considered this variation of the graph coloring problem in this work, because we noticed that the bandwidth coloring problem, the partial ordering based formulation is actually a much more elegant way to encode this bandwidth coloring problem than the assignment model. Because we have seen previously for the assignment model, we basically had a constraint for every pair of colors that is that has a distance of smaller than the edge weight. And now for the partial ordering model, the idea is that, okay, for every edge UV and every color I, we just need to encode the following. If the vertex U is assigned color I, then we just need to encode, okay, color vertex V needs to have a color of at most I minus the edge weight, or the other possibility is that vertex V has a color of at least I plus the edge weight. And the good thing about this partial ordering model is that we can encode these, enforce these constraints very directly with these with the pop variables, and then we end up with these constraints. So basically, this first term here says, okay, either we don't assign vertex U to color I, or if we assign vertex U to color I, we have that vertex V cannot be larger than color I minus the edge weight, or vertex V needs to be larger than I plus the edge weight minus 1, which means that it is at least I plus the edge weight. And then we only need a number of edges times number of colors. So we only need number of edges times number of color many constraints, unlike for the assignment model. And yeah, so if we adapt the partial ordering based model to the BCP, the number of constraints does not increase, which is an advantage for the specific problem compared to the assignment model. And we did some analysis on the number of constraints in the assignment bandwidth calling problem, and we basically saw that the size reduction of the number of constraints is in the order of the average edge rate of the graph. And yeah, now the question is if the size reduction of the formulation does actually help in practical runtime. And so I'm going to quickly go over the setup. Basically, we considered these two problems and graph calling and bandwidth calling problem, and used the Dymax benchmark set and the Geom benchmark sets for these problems because they're like the established sets. As a set solver, we use Kissat. LP solver, we use Garobi. The encodings and preprocessings were implemented in Python, and we used for graph calling, we used the standard preprocessing techniques, like we are pre-coloring a large click in the graph and also deleting vertices that preserve the chromatic number of the graph. And yeah, so for the results, first to compare the three ZAT encodings for the standard graph calling problem, we can see that they are pretty close, but okay, I won't go into detail what this POPA is. It's just a slight variation of the partial ordering model, but we can basically see that the partial ordering model solves. So this is basically one of these cumulative plots where we have the solved instances given a certain runtime, and we can see that independent of the runtime, the partial ordering models solve more instances than the assignment model. Now, if you compare this with the corresponding ILP models, because we thought this would also be interesting, we noticed even though these are basically the same models, just these are basically corresponding models, the SAT solvers seem to perform much better for this specific kind of problem than the ILP solvers, which is, I guess, an interesting insight. And also, like, the worst that model was still better than the best ELP model. And to put this into comparison with the state of art, we compared it with three methods: exact collars, GC, CDCL, and click-call-com, where click-call-com is a method based on the assignment ZAT model, but with some twists. We can see that the two best algorithms are the POP ZAT encoding and click-call-com, which performs very similar. And yeah, but the interesting thing is that click-call-com is based on the assignment model, but performs better than a pure assignment model. The question now would, for example, be what if we combine click-call-com with the partial ordering model, but we have not done that yet, maybe later. And yeah, here are all the results in one plot. Also, what we noticed is that the POP encodings are especially strong on the Queen and WAP types, type instances of the Dymax benchmark set. And now I think the more impressive results are actually for the bandwidth calling problem, because if we now compare the SAT models with each other, we can see that the partial ordering ZAT models basically dominate the assignment models, assignment ones. So we can solve much more instances, and also, like, after 100 of seconds or so, we solve more instances than the assignment model in like 1 hour. So it seems that the reduction in formulation size did pay off. Once again, if we compare it with the ILP models, the ZAT models are just better. And the interesting thing is, for the ILP models, the trend is actually inverse. So for some reason, the assignment for the ILP models, the assignment model is the best, and the POP models are worse, which is completely the opposite. We don't really know why yet, but it would be interesting to look into that. And compared with, like, the state-of-the-art approaches, included in Diaz et al., we can once again see that the SAT encoding just solves more instances. And also interesting maybe to note is that we solved these 6 instances from the Geom benchmark set for the first time to provable optimality. Yeah, so for the conclusion, we have seen that for the three models that we tested, that the SAT approaches outperformed the ones using ILP solvers. For the standard GraphQL problem, the three SAT encodings perform similar, but the POP encoding and the click-will-com algorithm, which is also based on SAT, performed the best. And the partial order models are especially strong on the WAP and Queen instances of the benchmark sets. For the bandwidth calling problem, the POP SAT encodings basically dominated all the other approaches. Now, for possible research directions, it would probably be very interesting to do a more in-depth analysis of some of the observed runtimes, especially why the SAT solvers seem to perform that much better than the ILP solvers on basically the same problems. It might give interesting insights to how improve ILP solvers using SAT techniques. Also, why, for example, the gap between the Simon SAT encoding and the POP encoding is so large for the bandwidth calling problem, because I don't think this gap is completely explained by the difference in formulation size. And another interesting idea could be to integrate these partial ordering models into other SAT-based frameworks. For example, as I mentioned earlier, the click-will-com algorithm is based on, so has this Simon's SAT encoding as a part of the algorithm, and maybe one could improve it further by substituting the Simon model by the partial ordering model. And if you want to try all these encodings out yourself, here's the code. And I guess this concludes my talk, and I thank you very much for your attention.
Thank you. We have time for a few questions. Yes, Moshe.
Seems that for all the encoding, all solver, you should just run it for 500 seconds, and after 500 seconds, you should just give up. If you go back your experiment, you don't gain much after 500 seconds. Can you comment on that?
That's true. And the thing is, the Dymax benchmark set contains a lot of instances that are for today's standards basically very easy to solve. So like, maybe I go to the graph coding.
So my conclusion is the wrong benchmark set, because it doesn't have enough diversity of difficulty. You have just, most of the benchmarks are just too difficult. It doesn't matter how long you run, you're not going to solve it. So you need a benchmark set that we see more interesting behavior than just running for 500 seconds. After that, just lie on the ground and cry.
I mean, the reason why we used the Dymax benchmark set is because it was easier to compare with the rest of the literature, because this was used a lot of the times in the literature. I'm guessing one could try to introduce a new benchmark set, because like a lot of the smaller instances of the Dymax benchmark set are not really interesting anymore. I mean, the Dymax benchmark set is pretty old, so it's already like 20 years or so old, and a lot of the instances aren't really that interesting because most of the approaches solve them in like 1 second, and there are some instances that are only really interesting for heuristics. But yeah, we just like wanted also to be able to compare to like literature, so we just used this as the standard benchmark set is just used. But yeah, it would probably be interesting to, for example, generate some other interesting instances.
Yeah, actually, this brings me to a question. So this looks almost like the plots we are using, but you have these straight lines. So I don't get like why you have, do these dots correspond to benchmarks you solved, or?
Okay, the dots correspond to how I wrote the PyPlot script. And basically we just check my script works like this. We check every couple of seconds how many instances were like solved, and then it does a point. So it does not really correspond to anything. I just wrote a suboptimal script.
But do you then, accumulate kind of how many, the time it takes to.
Yeah, basically, yes.
So it's not they are not run in parallel, or?
No, it's the result. So it's just how the plotting script works.
Okay.
The solvers do not run in parallel; they run after each other.
Okay, so you're saying the dots don't really make any.
The dots don't really have a meaning. I guess
Thank
you can, like, if you don't really can see the colors, they can help you differentiate between the models. But
I just wanted to make a very quick remark. I think it's absolutely 100% needed to muster some courage and throw out these old rubbish Dimex benchmark sets and create some new benchmarks.
Probably.
Because it's really a strange situation that for all of this graph coloring, there's so little relevant benchmarks available. And I believe it's a certain weakness of graph theoreticians also who don't think in that direction. And we in such should do much better and just create some really nice and foundational. Yes.
I mean, I would say there are like 30 instances that are interesting from the Dimex sets, but like then the other ones are like either too easy or interesting for heuristics. So yeah, maybe that would be a good idea. Keep the 30 and then just generate some new ones that might be more interesting.
Any other questions? I'm not sure if I overlooked this. Did you try to measure how much KISSAT benefit from symmetry breaking constraints that you had, and the same how much Gurobi benefits from that?
We did some experiments without symmetry breaking. The results are actually not that much different. It's mostly for graphs that, so the largest differences in symmetry breaking, you have them if for graphs that have small clicks compared to the chromatic number. For example, some of the Michelski graphs can only be solved with symmetry breaking because Michelski graphs have only clicks of size 2, and then the gap between the clicks and the chromatic number is large. So we have a lot of symmetries due to like the index, the relabeling of the colors. But once again, this benchmark set also has a lot of instances where the click is pretty large compared to the chromatic number. And then you just don't have that many symmetries, because if the gap between the lower bound and the chromatic number is low, then you can't really swap that many colors. So it's really instance dependent, but it helps. It helps in some way. So the difference isn't actually that huge, but it's definitely an improvement.
Okay. Well, if we don't have any other questions, let's thank the speaker again.
Yeah.
And this concludes our session.
All right, time for the same set of announcements, but with a twist. We will be heading to the banquet venue in the next 15-20 minutes. The shuttles are being readied. So by that time, if you want to freshen up, if you want to get ready, meet us at the reception, let's say by around 5:45, and we'll start sending the buses to the venue. Once again, the name of the venue is Hayat Place. That is in Hinjawadi Phase 1. If you want to know the exact location,